In this video, we'll actually see how we can perform sequence classification in a linear chain conditional random field. So far what we've seen is how we could compute the probability, the joint probability of a whole sequence of labels given an input sequence. So we've seen how we could compute in particular this nasty partition function using dynamic programming. And we've also seen how we could compute marginal probabilities, for instance, the marginal probabilities of a label at given position k given the full sequence. And again, performing this computation required the same dynamic program that we can use for computing the partition function, where we would compute these log alpha and log beta tables and use them in the computation of the marginal probability. Now here what we'll see is how we can actually perform classification. So if I give you a sequence of inputs, now I ask you to provide me a sequence of labels that you think is a good prediction for the sequence of the actual true sequence of labels that say a human or an expert would have predicted. So there are two options here. So we'll see two different procedures for performing that prediction. The first is perhaps the simplest. What we do is that for each position k, we compute the marginal p of yk given the sequence. So we compute the probability for any potential label yk of it being the true kth label in the sequence. And then as our prediction, we just say that in our predicted sequence, the label for the kth position is going to be the label that has the highest marginal probability. Now, so this is very similar to how for a neural network that would take just a single input, so not in the sequence prediction setting, we would just feed the input to the neural net. It would produce a output distribution for what the true label would be for the given input, and we just take the label with the highest probability. Now, we can actually show that this procedure for constructing a prediction sequence, so a sequence of labels that we would provide as an answer, corresponds to the prediction that minimizes the sum of classification errors over the whole sequence if we assume that our linear conditional random field, so our model, is actually the true model, is the true distribution that produced the sequence labels in our data set. So we actually, this gives some justification for using that procedure, and because this is an interesting concept, I actually will actually do the demonstration for why maximizing for each position the marginal distribution actually corresponds to finding this minimizing sequence of the sum of classification error if we assume our model is the true distribution. So what we want to do is find the expression for what is the predicted sequence y star that minimizes in expectation, so I should say this is the minimization in expectation according to our model, of the sum of the classification error for each position. So here we have the sum of the identity function of whether the true label according to our model, yk, so a true label in the sense that it's the label that based on the distribution of our model, is different from the predicted label at position k, so y star k. So we want to minimize in expectation that sum of classification error per position. So here I'm just writing explicitly what this expectation here is. It's the nested sum over the first label up to the last label of the sum of per position classification error, weighted by the probability according to my model that I would observe this sequence of labels y. So these yks here. Here I'm writing the fact that the minimization over all sequences y star is equivalent, so performing that minimization is the same as performing minimization sequentially over the first label until the last label. So it's this minimization over all sequences is the same as these nested minimization over first position, second position until the last position. Now here what I'm doing is that I'm going to take that, first I'm going to introduce this here, which allows me to just remove this parenthesis, and I'm going to change the order of the sums. So I'm going to actually sum first over the position k, and then sum over the value of the first label up to the last label. So that's why I have k here, then first label up to the last label. Okay, so that's all I've done. Introduce this here, and then change the order of the sums, of the nested sums. Now, I notice that this term here only depends on the value of yk for the position k that's indexed here. So I can actually, this is a constant with respect to y1, yk minus 1, yk plus 1, up to, so there should be 3 dots here, up to the last label. So I can actually push this here upwards in the nested sums, right in front of the sum over the value of the kth label and the sequence position k at which I'm measuring the error. Next, I notice that this expression here, that's just the marginal p of yk given this sequence. So I've taken the full joint distribution, well, conditioned on the input sequence, the joint distribution over the whole sequence y, but I'm summing over all the values that every label can take except the label yk. So that's the marginal p of yk given x. Next, I realized that this sum here over all position of what is essentially the expected error for that position, well, that's essentially the sum of the sum over y1 of whether I'm making an error by predicting y star 1 times weighted by the probability of actually seeing y1 as the first label, plus, so I do this sum over all k, so then sum up to the sum over y capital K of whether I'm making an error by predicting y prime y star capital K, weighted by the probability that the true label would actually be y capital K. Now, so I have a sum, and I'm minimizing over this sum for each label. Well, because each term in the sum actually depends on a single label, well, that's the same as minimizing the first term, so with respect to y 1, and actually, sorry, y star 1 only, and I don't need to minimize over the other terms because they're not involved in that expression, plus the minimization with respect to y star 2, up to the, so plus up to the minimization over the last label of this term here. Okay, so that's because the minimization over all labels for a term that depends on only one label is the same as minimizing over a single position or a single label. And so now the we notice that, let me remove some ink. So we notice that this expression here, which is the sum of 1 if y1 is not y star 1, weighted that by the probability of observing y1. So that's the sum of the probability of y1 for every case except when y1 is equal to y star 1. So in other words, so that's the probability of the first label not being y star 1, which is equal to 1 minus the probability of the label being y star 1. And so similarly, for this term, we also get 1 minus the probability of y star capital K. And then finally, performing each minimization, minimizing 1 minus this term is the same as doing 1 minus the maximum of this term. So indeed, this is a constant, so I can't minimize it really. The choice of y star 1 won't change the value of 1. And so I can introduce this here. And the minimization of the negative of something is the same as minus the maximization of that something. So that's what I have here. So this is equivalent to this. And in particular, the argmin here, or the argmax, is the argmax here. And in other words, it's the sequence where the first label is the one that maximizes the marginal probability for the first element in the sequence. And then same thing for the second label, third label, up to the last label, which in my prediction should be the label y star k, which maximizes the marginal probability of the label at the last position, at the position capital K. Okay, so this ends our demonstration that if I assume the true labels were generated by my model, my linear conditional random field, then if I wanted to minimize the expected classification error per position, the right thing to do would actually be to produce the sequence of all labels that maximize the probability of being observed according to my model for each position, and constructing my prediction by concatenating all of these all of these labels. So that's the first option. Another option would be to do the equivalent of what we were doing in the non-sequential prediction part. That is, I'll just produce as my sequence output the so actually this should be a star here. I just produce as the sequence output the single sequence with the largest probability, the largest joint probability condition on my input sequence. And so I'll go rapidly over this, but it turns out that much like we've seen a way of actually summing over the something like this term, the exponential exponentiated sum of log factors, we can also perform the maximization with the dynamic program. So we'll do what we get essentially is a variant of the Viterbi decoding algorithm, where in the forward pass, so much like in the alpha dynamic programming, where for the log alpha we had log sum exp operations, well, in this Viterbi decoding algorithm, we replace those by the maximization with respect to y prime k instead. And then we fill the table with those values. And in fact, if you think about it, log sum exp is actually can be thought of as a smooth version of the maximization operation. And that's because of the exponential here, the term that is going to dominate this sum is going to be the term that is largest, because the exponential increases very rapidly with large values of its argument. And then taking the log, we go back to the original scale, and so really the term that's going to dominate this whole term here is going to be the maximum. So so that's just, you know, a nice fact to know about the relationship between the log sum exp and the maximization. And but so yeah, so we take the forward pass, say in the dynamic program that computes the log alpha table, and we replace the log sum exp operations by a maximization. And then in the backward, then we have to produce a backward pass. And in the backward pass, well, we'll essentially compose our decoded, so our predicted sequence by finding the last label that maximizes the value in our table, and then following backward the trace of the max operations. So following backward the links that are going to correspond to what were the argmax when I was performing this maximization here. So more specifically, let's look at the pseudocode for this algorithm. We first initialize the value of my alpha star. So I'm going to use star for the dynamic program, the Viterbi decoding algorithm that is going to fill this alpha star table as opposed to the alpha table. And notice that here we have a maximization instead of a log sum x operation, where we do a maximization over what would be the argument of the log sum x operation in the computation of the log alpha table. So I initialize the first column of my alpha star table by performing this maximization, and I also remember for each value of y prime 2 what was the actual value of y prime 1 that was maximizing the sum of the log factors. So see here, this is the same thing as here. So this is just the argmax of this maximization. And then, much like in the log alpha table, I'll go from the first, from k equals 2 to the last, till the last column, and then for each value of the label, I'll perform the similar computation where I've replaced the log sum x by the maximization. And here I have unary factor, pairwise factor, and the alpha star, so the value at my previous column in my alpha star table. And similarly, I'll remember what is the argmax. So I'll put that into this other table, which where I put the arrow to distinguish it from the alpha star table. And then finally, if I want to know what's the probability of the most likely sequence y star, so what's the maximum of y star of p of, this should be a y star also. Well, it just corresponds to taking the maximum over this expression here. And so that's actually not exactly taking, I said taking the max over the last column, but that's not exactly true. It's the max over the last column plus the unary log factor for the last position. And then to perform decoding, that is to actually construct my predicted sequence y star, I'll take again the argmax of this maximization here, so the argmax of the unary factor at the last position plus the alpha star for the last column of my alpha star table. So that's going to be the predicted label for the last position. And then I'll go backwards from the previous to last position till the first. And what I'll do is that y star k is just going to be what was the argmax. So we see the arrow here. What was the argmax when I performed the maximization for alpha star k, assuming that the value for y star k plus 1, so for y prime k plus 1, is actually y star k plus 1, which is the value y star in my sequence that I computed in the previous iteration. So we see that by initializing y star capital K here, well, I always have a value for that. So I'm going from right to left using my previous y star value to construct my, I guess the value of y star at the position to the right to construct my prediction for the current position K, and then going from right to left. Okay, so this is how I get, this is an algorithm, but that is also, that has, a nice complexity of, that's polynomial in K and capital K and capital C for computing, constructing a prediction, and so classifying a whole sequence of inputs and producing a sequence of labels for my sequence of inputs. So the two types of predictions, this Viterbi decoding approach and the other one that maximizes the per position marginal, are two valid predictions to perform. If we really care about the sum of per element, the sum of per element classification errors, we might want to prefer the first procedure. But if instead our prediction error, if the way we evaluate the performance of our classification sequence classification system is different, and so for different systems, like in speech, for instance, we'd be more interested in a phone error rate, which is more complicated, then performing this Viterbi decoding procedure should be preferred, because then we're not maximizing the sum of per position errors.